Lecture 12, parts 3. And in the previous two parts, we talked about how to compute the principal components for the PCA problem. And the main idea is we have a bunch of data points like this, and we want to find the direction that captures the largest variation, and then find the perpendicular ones that captures the second largest variation, and we call this U1 and U2. So what we haven't talked about is how to actually find the new features. So we have originally we have two-dimensional feature, and suppose we only want one new feature, what should that feature be? So the most obvious one should be, the most obvious idea should be just do the projection and use that projected vector length as our new features, and indeed that's what we'll do. So here, this is just the length of the projection. So remember at the beginning, we have a formula for this. It's just U1 transpose xi. So say this is our point xi. And if we multiply by U1, then it's this vector here. If we don't multiply it, then that will be the length. And if we want both of them, then we can also project it here on the second principal component, and that value will be U2 transpose xi, and then we can have as many as we want, and this is basically the new feature space. So the original feature space is m-dimensional here. If we choose a k that's significantly smaller than m, then we have a smaller dimensional feature space with a fewer features. So the next thing we can do is basically we can just use these as our features, as our training data, and then we train some supervised learning algorithms, mostly SVM. Sometimes maybe we want to use neural network, but neural network can construct new features by themselves, so we usually have SVM paired with this PCA. So that's how to generate the new features. And something else I want to talk about is the reconstruction error. So it's another interpretation of what we're doing. So before, what we were doing is maximizing kind of the variance, which is UK transpose sigma UK. And equivalently, we can minimize something called the reconstruction error. So basically, the amount of mistake that are going to occur if we want to reconstruct the original data points using these principal components. So let me talk about it. So suppose we use the principal component ui and we want to reconstruct our xi, then the best we can do is to use the projection, right? So the reconstruction error here would be just the norm of the difference between xi and ui, which is exactly this. So this vector here is our UK transpose xi UK. So their difference, and take the length, the norm, it's basically this part, and we're calling that the reconstruction error. So maximizing this is basically the same as minimizing that, it turns out. I'll not go through the mathematics, but you can just remember this as a result. They are equivalent. So we don't need a diagram. And one application to what I just said is eigenfaces. So what we can do here is basically we can figure out some of the principal components, and we'll call these principal components of phase images. For example, we can use pixel intensity to represent these phases. Note that the principal components, they have the same dimension as the original images. So these principal components are also phase images. And we're going to call these phases the eigenfaces. So basically the principal component phases. And we can use these principal component phases to reconstruct our original image. And the way we're going to do it is, first, any vector can be written as the sum of its projection into the space that has the same dimension. Let me give you an example. So suppose we have these two dimensions, and we have a new vector, say our xi here. And if we project it to the first principal component, and then the second. If we add these two up, remember the way to add them up is to just move it to here, and then we can get the same thing, right? So if we add up the projections from the first dimension plus the second dimension plus the third dimension, then we can get this original vector back if we add up all of them. However, if we only use k of them, and k is, say, smaller than m, if we choose these principal components properly by minimizing, again, the reconstruction error, it means the remaining components, k to m, the amount of mistake we're going to make is kind of small, so they have smaller impact in reconstructing the face, or in reconstructing the original vector. So basically, we can get rid of all of these and just use the first k of them because they capture the most of this image here. We can actually do the same thing for the faces. So what we are doing here is we can just store these principal component faces. These, remember, these are faces, and these things are just numbers. They are dot product between a vector and another vector, so they are just coefficients, and they are just scalars. We can just remember these scalars that represent this face, and we can use these principal component faces or eigenfaces to n plus these numbers, these few k numbers, to reconstruct the original face image. And let's actually try it, because talking about it doesn't make any sense. So one example, on one of the training sets, we can get, say, 30 principal component faces, and if you actually plot them, most of them look like faces, right? So that's the principal component eigenface number 1. So the most important face is this one, and this is the second most important face. And then, so what we're saying is, if you have a face image of any person, you can write it as a linear combination of these faces. So a number multiplied by the first face plus a number multiplied by the second face plus a number multiplied by the third face. So that's what's happening. And it may be hard to believe, but let's actually look at the example. So suppose the original image is like this. If you only use one eigenface, so I think it's on a different data set, so that's why it looks different. So the first principal component face. But in any case, if you only use one, then it looks like someone else. If you use 20, then it's already somewhat look like this person with kind of glasses here. If you use 40, then it's a lot better. It actually looks like the original person, right? So, and here, if you use 50, it is really, really close to the original image. If you go back and look at the original image, they do look, say here, the same. So you only need to remember 50 numbers to remember a person's face. So that's what we mean by eigenfaces. And another example is here. One face, again, the same thing. 20 faces, more like a particular person, and 40 faces, and again, 50 faces. And 80 faces, we basically have the original image back. Okay, so that's one application of we represent faces by just a few numbers, and we use the eigenfaces constructed by a training set to represent, say, any face. And here we can use these, and we can use SVM on these features. These features are basically just the coefficients, and we can use it to detect all mostly recognized faces, because, as I said, each face has unique coefficient, and we can use these coefficients to, say, identify the person. Okay, so that's one application. And as what we have done before, we're going to extend this to use some kind of neural network and add some kind of nonlinear activation. And the idea is called autoencoder. So I remember talking about this in one of the previous lectures, but in any case, I want to repeat it. So if we have a neural network, and we have the input is a face, and the output is also a face, and if we have one hidden layer, or we can have multiple hidden layers, but I'll just draw one of them. with k hidden units, then what we can do is we can train a neural network that with this input and with the same output fully connected. And after training, what we have is basically a face is encoded by k numbers. And these k numbers, independent of the original image, if you look at only this part, none of the weights are connecting the original image to the output. So we can basically only use these k numbers to reconstruct our original image as much as possible. Right? So here, what we're training is we're training to get k hidden unit values so that we can reconstruct the original data set. And these k hidden units values, they will be our new features. So that's what we can do here. And we can actually break this neural network into two parts. One is the encoding part. So after we train the whole thing, after the weights are already correct, we can break this part to just encode the faces. Or we can just use this part to reconstruct the faces. Right, so, and this structure is called autoencoder, and it turns out that is this structure actually, if you use linear, not LTU, but linear activation. What I mean by linear activation is no activation, basically. So A is just WX plus B. If we do that, it actually, these numbers would approximate PCA. So basically the linear version of autoencoder is like PCA. And if we add some kind of non-linearity, like for example ReLU, or we can do a logistic, there is kind of a non-linear version of PCA. So it gets more powerful because it can represent stuff non-linearly. And well, these structures with the same input and output, they are called autoencoders. And the training is exactly the same. Everything is exactly the same. It's just a different network structure. Okay, so I already had a diagram. And the next thing is we'll talk about kernel PCA. So remember we talked about kernel SVM. So we're doing exactly the same thing here. We're going to apply some kind of feature map to the original features, maybe to make it into a higher dimensional space, even higher dimensional space, and then we can do PCA on those features. And the problem is, of course, we want something like the Gaussian kernel. So it basically transforms these things into infinite dimensional spaces. We cannot deal with infinite dimensional matrices. So we can use the same kind of dual optimization idea to compute PCA. So the same idea with support vector machine that I just mentioned and didn't really go into the details here. Here we're not going to go through the details as well. So I'll just say that it's a similar technique as the support vector machine. We'll not deal with these feature maps and we'll use the kernel matrix instead. Okay, and that introduced some kind of non-linearity. So the kernel PCA is also another non-linear dimensionality reduction method. So these are all I want to talk about PCA. Let's actually talk about another completely different algorithm, and it's more like a embedding idea as opposed to a dimensionality reduction. So the reason I still want to talk about it is it does reduce the dimension into usually 2 or 3 dimensional spaces. So what this algorithm named T-distributed stochastic neighbor embedding is doing is we want to visualize a high dimensional space. What I mean by high is like 100, 500 dimensional spaces. We want to put them into 2D or 3D, and we want to visualize basically those data sets. Okay, so the idea here is more related to embedding. So let me first talk about this embedding idea. So if we want to embed, say, a 2D shape into 1D, if we want to preserve the distances, so by the way, embedding means just preserving the distance structure. So here, if we have 3 points, and they are equally distant from each other, we want to embed this into a one-dimensional space, basically 3 points. It's impossible. If we only have 2 points, then yes, it is possible, but 3 points is not, because we want the distance between these two to be the same. Also, we want that one to be the same as well, which is impossible in a 1D space. So that problem is figuring out what kind of embedding is the closest to a structure like a triangle, which I think is something like this. So similarly, we can have the 3D version. So imagine 4 points. Each pair of points is equally distant from each other. So we have a 3D structure like this. So my drawing is not great. Basically, we have these 4 points. It's like a pyramid. It's just the base of this is a triangle. There is actually a name for this, but I don't know it. In any case, if we want to embed it into 2D, then we may want to draw something like this. But it's not great because these 3 are not equal. But in 3D, they are equal. So every pair of points, they are equal distance to each other. And here, it's impossible to do that. But maybe the best way to represent it is something like a shape like this. So embedding is basically the idea of figuring out how to draw things in lower dimensions. And let's actually talk about some examples. So the first few are 2D to 2D, so they are not interesting. They're only interesting mathematically. Let's actually look at a 3D one. So if we want these 2 rings, so if you look at this very small 3D diagram, there are 2 rings, and if we want to put them into 2D, let's look at how it's going to do it. It's just going to stop here as 2 circles. So it does not preserve the global structure. It just preserves the local structure. So if you look at each point in relation to, say, 10 of the neighbors, then each point is related to the neighbors by a circle. So it is actually correct. So if you only care about the 10 neighbors and preserving that kind of local structure, then you are preserving the local structure by just plotting them as 2 circles instead of representing how they are related. But if we care about more points, more nearby points, we can increase the perplexity value here, say 50, and let's see what's happened. And it actually preserves this connected ring structure. So these 2 are connected this way. Let's try something in between, maybe say 25. So it does kind of preserve that connected structure as well. If you look at 2 different circles, like disconnected circles, it will still be displayed in 2D that way. So here you can see that we are actually using some kind of gradient descent, and there is actually the parameter epsilon, which is basically the learning rate for gradient descent. So we're training these using gradient descent, and there are some more interesting 3D points, 3D point clouds, and say that one is, I can actually see what it looks like in 3D. But in 2D, it looks like just a curve. And this, I think, is kind of a cloud. So in 2D, it's kind of a cloud as well. So another maybe interesting one is this one. This looks like 3 rings, but connected in a strange way. So I think it's easier to visualize this in 3D. Let's see what happens in 2D. Okay, so it does capture the structure very well, but let's change it to care about more neighbors. I think it will do the same. Yes. And let's actually try something with low perplexity. Okay, slightly different. And I think if we try it with even lower perplexity, then it's going to be something different. Yes, so it expands it to a circle. Because if we only care about, say, the two close neighbors, these three knots can actually be expanded because the two nearest neighbors are just along that curve, and it can be expanded to a circle like this. Maybe let's try slightly more. Okay, it goes back to the not structure. Actually not. Actually, it converges to something else. So it's kind of behavior is strange, but the basic idea is, well, how many neighbors do we care when we say we want to preserve the distance? So that's the important idea behind this T distributed stochastic neighbor embedding.